Okay, this is a screencast that I put together just to go through the calculations we went through last Thursday to give you a second presentation of it and also allow you to go back and revisit what we covered in class. So we were basically drawing cards out of deck B. And what we wanted to know is we wanted to know what the sample mean of deck B was and what the range of variation would be, and we wanted to calculate the 95% confidence interval. So what we essentially had was we had a series of observations. Somebody drew a 1, somebody drew a 1, a 2, a 4, and a 4. And we can represent these things essentially as symbols mathematically. This is the first observation from the B deck. So it's y subscript 1b. This is y subscript 2b, y subscript 3b, y subscript 4b, and y sub 5b. And this is just the symbolic shorthand that we use to represent observations that we make when we're taking a sample. And you might see, or you will see in this class, that we used symbology like y sub I j. This just simply means that this is the ith observation from the jth treatment. And in this case, we're treating the two decks as different treatments. So y sub 1b is the first observation from the B deck. And so if we want to know what the average is, we simply add these up. The symbol for adding is sigma, the uppercase sigma, and we're adding all of the y values that are in the B deck. And this would be 12. If you added those up, it would be 12. And then to calculate the sample mean, we would simply sum all of the y values up and divide that by the number of values that are in deck B. So this would be the sample mean of B. And so this is 12 divided by 5, which ends up being 2.4. And so this is kind of your first equation that you need to become familiar with, which you probably already are, which is the equation for a sample mean. But now what we want to do is we want to calculate sample variance. And sample variance, we use the symbolic shorthand of S squared. And the reason that it's a squared S is because it's a series of squared deviations from the mean. So what do I mean by that? Well, we basically take the value that we observed, in this case 1, and we subtract from that the mean that we calculated. Take the next value that we have and subtract 2.4 from that. The third value, subtract 2.4. The fourth and fifth values and subtract 2.4. And I don't know why I wrote 2.5 there. I'm going to erase that. And actually, I erased too much. 2.4 and 2.4. Now, we already discussed how if we do that and we add those up, they would all sum to 0 because the mean serves as the fulcrum of the weight of the data set. So you have as much on the negative side of the fulcrum as you have on the positive side of the fulcrum, and they'll just sum to 0. So what we have to do is we have to take each of these and we have to square them. And when we square them, it will take all of the negative values, which are those first three, and convert them to positives, and then these positive values would stay as positives. And so what we're basically doing is we're taking y sub 1b, we're subtracting from the mean from it, and then we're squaring that difference. And then once we have all those differences calculated, we're going to sum those, and that ends up being the numerator of the variance. So let's just do this. This would be negative 1.4 squared, negative 1.4 squared, negative 0.4 squared, positive 1.6 squared and a positive 1.6 squared. That is 1.96, 1.96, 0.16, and 2.56 for the last two. And when we add all of that up, that gives us a total of 9.2, which is the sum of the squared deviations from the mean. And when we calculate sample variance, it's the sum of the deviations of the values from the mean divided by the degrees of freedom for variance, which is the sample size minus 1. Now, this is the next formula that you might want to commit to memory if you're into committing formulas to memory. But I would rather you learn how to do what's up here and then be able to generate the formula if anybody ever asks you what the formula it is. I would much rather you be able to do it than you be able to write the formula for doing it. But what I want you to notice is that this formula for the mean is the sum of a bunch of things divided by the degrees of freedom. So it's the sum of a set of things divided by the degrees of freedom for the mean. This is a sum of a bunch of things divided by the degrees of freedom, in this case, the degrees of freedom for variance. And so you can think of the average as being the average, but you can also think of variance as the average deviation from the mean. And so you're going to see that this parallelism of formulas happens a lot as we go through this. So this whole thing ends up being 9.2 divided by 4, which is 2.3. Now, standard deviation, I gave you the calculation for in class. It's simply noted as S, and it's the square root of the variance. And then I gave you the standard error for the mean. Standard error of the sample mean. And I gave you that equation as the standard deviation divided by the square root of n. But if you want to skip calculating the standard deviation, you could also just as easily express this as the square root of the variance divided by n. And both of these will give you the same value. And so if we take the square root of 2.3, that gives us 1.5166. And if you take the standard deviation divided by the square root of n, that's 1.5166 divided by the square root of 5, and that would equal 0.6782. But you can check my math on this. If you also just take the square root of 2.3, which is the variance, divided by 5, that will also give you 0.6782 because you're doing the same thing to both the numerator and the denominator. So then we use this standard error of the mean to calculate a 95% confidence interval. And the 95% confidence interval is simply the mean of B plus or minus the t-value associated with this sample size multiplied by the standard error. And so in this case, we can look up t. You would go to a statistical table, or you can look up calculators that do this online. We want for an alpha level of 0.05 and 4 degrees of freedom. And that ends up being 2.776. So to calculate the upper limit of the confidence interval, we would take the mean, which in this case is 2.4. We would add to that 2.776 multiplied times 0.6782. And if you do that math out there, you would get an upper limit of 4.283. And the lower limit would be 2.4 minus 2.776 times 0.6782, and that would be 0.517. So what we've done here is we've represented this as a midpoint of the data, in this case represented by the mean, the weighted average of all of those values, and then the upper level and lower level of the 95% confidence interval. So we can come over here to the next page and we can make ourselves little number lines starting at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and we can make ourselves a number line. And then we can plot these numbers on here. So the mean of B is here at 2.4, and the upper limit of B is 4.2, so about right there. And the lower limit of B is 0.5, which is about right there. So this would constitute the 95% confidence interval for the cards that you guys drew from deck B. Now, when we look at deck C, and so I'm going to do deck C in a different color, we can go in and we can look at deck C. The values that we have from deck C are basically 8, 9, 2 12s, and a 13. The number of observations that we have is still 5, but we can represent these as the first value of deck C, y sub 2c, y sub 3c, y sub 4c, and y sub 5c. Those are just the first, second, third, fourth, and fifth observations from deck C. And we sum all of those up. That gives us a sum of 54. And to calculate the mean of deck C, we would take 54 divided by 5. That would give us 10.8. Now, to calculate sample variance, we just go through the same steps. 8 minus 10.8 squared, 9 minus 10.8 squared, 12 minus 10.8 squared, 12 minus 10.8 squared, 13 minus 10.8 squared. This ends up being 7.84, 3.24, 1.44, 1.44, and 4.84. That sum is 18.8. That once again is the sum of the squared deviation of the observations minus the mean. And so now that we have that sum, we can divide that sum by the degrees of freedom for the variance, which is the sample size minus 1, which is a sample size of 4, and that will give us the sample variance. So we can take 18.8 divided by 4, and that will give us 2.168. Now I'm going to just skip ahead and do the standard error using the square root of everything. So the standard error of deck C is the square root of the variance, 2.168, divided by the sample size, which is 5. And when we do that, we get 0.9695. Then to calculate the 95% confidence interval, we will get the mean of C plus or minus 2.776, because it's the same sample size that we had before, times 0.9695. Since the mean was 10.8, this will be plus and minus 2.776 times 0.9695. That means that the upper limit will be 13.49 and the lower limit will be 8.11. So now we can go back up to this number line that we have up here at the top. We can say, okay, well, where's the mean for C? The mean for C is right here at 10.8. Well, what's the upper limit of the 95% confidence interval? It's 13.49, so basically here it's 13.5, and the lower limit is down here at 8.11. So we can essentially make a 95% confidence interval, and you'll notice a couple of things. The 95% confidence interval is larger because the variance was larger, and so we should expect the confidence interval to be larger. But what I want to call attention to is the meanings of the 95% confidence interval. When we talk about a 95% confidence interval, what does it mean? Well, there are two meanings, and we touched on this in class last Thursday. One meaning for what a 95% confidence interval is this. Within that range, the 95% confidence interval should include 95% of all sample means that are drawn from that population. Assuming that you're drawing the same sample size, in this case, a sample size of 5. This is the most useful of the definitions for what a 95% confidence interval is, because what it allows you to do is it allows you to look at this and it allows you to say, okay, well, what is this value here? Well, it's 10.8, and we can ask ourselves, could we have drawn that 10.8 from this population? And it's very unlikely because 10.8 doesn't fall between 4 point whatever and 0.5. And so it's very unlikely that the mean of C would have been drawn from the population that produced the mean of B. And in a similar way, we can ask ourselves, could we have drawn the mean of B from the population that produced the mean of C? Well, no, because once again, the mean of B is 2.4, which is way lower than the lower limit of the 95% confidence interval of 8.11, which is the lower limit of the confidence interval for sample C. So when we think about this, do not think about how much the confidence intervals overlap. So I'm going to put this in all caps. Do not pay attention to the overlap of confidence intervals. They will lead you astray sometimes. Pay attention more to, does the confidence interval of one sample include the mean of the other sample? Does the confidence interval of this sample include the mean of the other sample? If they don't, then those two means are probably different. If they do, then those means are probably drawn from the same underlying population. Now, there is a second way in which you can define what a 95% confidence interval is. The second way is basically there is a 95% probability that the population mean is in that interval. And I don't remember what the exact values were, but I think the population mean for B was something along the lines of 2.3. And I think the mean of population C was something around the lines of 10.2. I'd have to go back and I had it written down in my office, but anyway, it's something in this range. We can revisit that in class tomorrow, and you can see that both of these values are completely right in the middle of those 95% confidence intervals. But this is a less useful thing because biologists are seldom asking what does the population mean of something. Biologists are typically asking, does one mean differ from another mean? In which case, it's this definition here that serves you best. So hopefully that is a good review of the calculations that we pretty much completed in class on Thursday. This just serves as another way in which you can go back and access that information. So look forward to seeing you on Tuesday, the 9th of September, and have a good evening until then.